Hi everyone, today we're going to talk about the pH curve of weak acid strong base titration. Now here's the problem. We're titrating 20 milliliter of 0.1 molar acetic acid with 0.1 molar NaOH. Please watch this video carefully because I know you'll be doing this in your lab and it will be helpful for your calculations. So first of all, we need to calculate the volume of NaOH needed to reach the equivalence point. And we write the net ionic equation, which is hydroxide ion with acetic acid to form water and acetate ion. The sodium is the spectator ion that will get dropped out of the net ionic equation. Now at the equivalence point, stoichiometrically, moles of acid is equal to moles of base, so we use MAVA is equal to MBVB as a formula. Plugging the numbers in, we can now calculate the volume of the base to be added, which is exactly 20 milliliter. Okay, so now we're ready to calculate the 4 points along the titration curve initially. When there's no NaOH is added from the burette, now we only have the weak acid in the flask ionizing partially, according to this equation. Therefore, we take the Ka value and set it up 1.8 times 10 to the minus 5 equal to x squared over 0.1 minus x, x being the concentration of the hydrogen ion and the acetate ion, or the change, and 0.1 molar is the original concentration of the acetic acid. Solving for that, hydronium ion is 1.3 times 10 to the minus 3 molar, and therefore pH based on that is 2.89. Okay, now at the point B, halfway to the equivalence point, after 10 milliliter of 0.1 molar NaOH has been added. So we calculate the millimole of the acetic acid, which is 2.0 millimoles, the hydroxide ion, which is 1.0 millimoles. Now we write the net ionic equation, and we set up the ice table, attach the values, and the hydroxide ion is the one that's used up, and we take away 1 millimole from the acetic acid, add 1 millimole to the acetate ion. So we have 1 millimole of each remaining, and they are equal in millimole, they're equal in concentration over a volume of 30 milliliter, which is 0.033 molar. Now we use Henderson-Hasselbalch equation to find the pH, which is pKa plus log of the ratio, and since they're equal molarity, it is log of 1, which becomes 0. So pH is 4.74, which is pKa at halfway to the equivalence point. Now at the equivalence point, we have added 20 milliliter of NaOH. So the millimoles of the weak acid and the hydroxide ion are both 2 millimoles. Writing the net ionic equation, attaching the values to the ice table, we would have used up both the hydroxide ion and the acetic acid, but formed 2 millimoles of the acetate ion. Now that's over a total volume of 40 milliliter, which becomes 0.05 molar. And now we have the salt that contributes to pH when it hydrolyzes in water. Now the salt would hydrolyze in water to form the weak acid and the hydroxide ion. So we attach the values to it at equilibrium. And then we use Kb value to solve the problem because of the formation of hydroxide ion. And Kb is calculated by Kw divided by Ka. So we set it up now and solve for x, which is 5.3 times 10 to the minus 6 molar for the hydroxide ion. And therefore pOH is 5.28 and pH is 8.72. Notice that at the equivalence point, pH is no longer than 7. It's slightly basic. At point D, beyond equivalence, after 30 milliliter of NaOH has been added. So we have 2 millimoles of acetic acid, 3 millimole of the hydroxide ion. And when we set up the ice table, we find out that we have 1 millimole of the hydroxide ion remaining. That dictates the pH. Now the acetate ion is so small compared to the, isn't such a weak conjugate base compared to the hydroxide ion, doesn't really affect the pH that much. So taking the concentration of the hydroxide ion, 1 millimole in 50 milliliter, which is 0.02 molar, and the pOH therefore is 1.7, and the pH is 12.30. This is in the basic region when there's excess hydroxide added. Now let's take a look at the pH curve. You notice that at point A, we have the pH dictated by the ionization of the weak acid. At point B, which is halfway to the equivalence point, both the weak acid and conjugate base are equal in concentration. And then at point C, at the equivalence point, pH in the slightly basic region, 8.72. Now there's a buffer region between point A to point C because you have both the weak acid and conjugate base present. From A to B, the weak acid is greater in amount than the conjugate base. But from B to C, then the weak acid is in smaller amount than the conjugate base. At point C, the equivalence point pH is dictated by the hydrolysis of the salt formed. And finally, at point B beyond the equivalence, pH is dictated by excess hydroxide ion in the solution. Notice that there's a shoulder, okay? From point A to C, that's the buffer region, resisting change in pH. And the change in pH at the equivalence point, the slope is not as steep as the strong acid, strong base. So characteristics of the curve, recapping it, beginning pH 2.89 determined by partial ionization of the acetic acid. Buffer region goes from A to C. There's a shoulder here due to the presence of both components in the buffer. The rise in pH is very gradual near the equivalence point, not as steep. Now from point A to B, the concentration of the weak acid greater than the conjugate base. At B, halfway to the equivalence point, the concentration of the two components are equal. pH is pKa 4.74. Continuing from point B to C, now the weak acid is in smaller concentration than the A-, the conjugate base. At the equivalence point, all the weak acid and strong base have been consumed. pH is determined by the hydrolysis of the A- ion, which is 8.72. At point D, beyond equivalence, pH is 12.3, determined by excess of hydroxide ion. Analysis of the curve. When you are given a pH curve as such, there are two pieces of information that you can determine from it. One would be the molarity of the unknown acid using MAVA and MBVB formula. And now you can extrapolate at the equivalent point C, there are 20 milliliter of NaOH added. So if we know the molarity and the volume of the NaOH, and we know how much of the HA we have in the flask originally, we can calculate the molarity of the weak acid. We can also determine the Ka value of this unknown acid because if we go to halfway to the equivalence point, which is 10 milliliter on this particular curve, and we read the pH which is about 4 to 5, about close to 5 but higher than 4, then we can estimate that being the pKa value, and we take the anti-log, which is 10 to the minus 5. So summarizing again one more time how we do the calculation, initial pH is based on ionization of weak acid, use ice table, Ka, and initial concentration of HA to find hydrogen ion. Between initial pH and equivalence point, solution becomes a buffer. Use stoichiometry to calculate amount of the buffer component, and use Henderson-Hasselbalch equation to calculate pH. Halfway to the equivalence point, buffer components are equal. pH is equal to pKa. At the equivalence point, pH is based on hydrolysis of the salt form. Use Kb to find hydroxide ion. Beyond equivalence point, pH is based on excess hydroxide ion present. If you compare the pH curve between a strong and a weak acid, you'll notice that initial pH of strong acid is lower than that of the weak acid because we have a higher concentration of hydrogen ion. The buffer region exists in the weak acid but not the strong acid. And the amount of hydroxide added to reach the equivalence point are exactly the same given that we have equal molar, equal volume of the two acids. And pH at the equivalence point is higher for the weak acid, about 9, than that of the strong acid, which is about 7. The effect of Ka on curve. Now here is a curve that we should pay close attention to. It results in different shapes of various weak acid, 0.1 molar, titrated by the 0.1 molar NaOH. you notice that they take the same volume of NaOH to reach the equivalence point. And the weaker the acid, the greater is the pH value at the equivalence point. And the vertical region around the equivalence point becoming shorter as acid titrated becoming weaker. Now here we have a titration of a polyprotic acid, which is sulfuric acid. So when you have the hydroxide neutralizing the first proton from the sulfuric acid, we form the hydrogen sulfide ion. Then the second proton is further neutralized by more hydroxide to form the sulfide ion. Now when you look at the pH curve very carefully, you notice that there are two equivalence points because there are two protons to be donated. And it takes exact amount of OH minus 25 milliliter to reach each equivalence point. Equivalence point 1 is about pH of 5. Equivalence point 2 is about pH of 9 plus. And you also notice that there are two halfway to the equivalence point, so we can estimate the pKa1 as to be close to 2 and the pKa2 as to be between 7 and 8. And therefore, we can now calculate the Ka1 and Ka2 value from such a titration curve. To summarize what we have learned today, we learned how to calculate the various pH values of a weak acid strong base titration. We learned the characteristics of the pH curve. We determined the molarity and Ka value of the weak acid from the pH curve. We learned the effect of acid strength on the shape of pH curves. And finally, we learned the characteristic of a polyprotic acid pH curve titration. I hope that you find the video helpful. If you like it, please give us a like and please subscribe to our channel. And I hope to see you again real soon.